Okay. So what I have here is one of those survival lights with the crank on it that you can recharge this cell. This is pretty much a 2032 that happens to be rechargeable, and has like a lever that folds into the body. I'll put a picture up on the screen of one of these things. I got this out of a truck that I was taking apart that we bought. We're going to end up using it as a camper. It was an old dog catcher truck, and this thing was in there, and the battery's pretty much dead, and it was real filthy. So I just took it apart, ripped the electronics out. So we're going to try and kind of reverse engineer this thing. I am absolutely by no means a professional, but I have a meter and I have a data sheet for this chip, so we're going to try and go through and see exactly how this thing works. So without further ado, get the meter. Okay, and the chip that's on this thing is a D1802 S23, so you can find, I think what I got on here is a 2SB or a 2SD1802 data sheet, something like that. But there's a couple variants of this. This data sheet happens to be for the one made by Sanyo, which has a diagram that looks exactly like this chip. So this may be a Sanyo chip. So the way they have the diagram for the switching test circuit, they have 100 microfarad and a couple resistors, and I can see resistor here, current limiter for each LED, and one capacitor. So I think they're just using this as a switch. On the data sheet, you can see the ratings here are you can supply up to let's see, up to 6 volts on the emitter to the base, and then on the collector to the emitter it'll do up to 50 volts. So it has curves in the data sheet for with and without a heatsink. So this is a pretty overpowered switch for what's going on here. So I don't know if they do that because the crank mechanism might be capable of outputting enough voltage to warrant something like this. I'm not sure, but obviously they're taking AC, because this right here happens to be the this is the motor, and the crank went on, something like that. You spin the crank and it spins the body of this electronic motor around the coils, and that outputs an AC voltage. So there is rectifying going on here. That's why there's so many diodes. And then the switching, I believe, is just to take the 3.6 and throw it to the 3 LEDs. I don't think this big chip is doing anything with the actual AC current. I think it's just switching the DC for the lights. So this button on the back, we're going to go ahead and take the meter and see what this button actually does. It's got 3 poles on it, and it acts as 2 positions in the light. So I'm guessing this is a kind of a 2-way switch. You'll have off 1, off 2, off 1, off 2, something like that. So I'm guessing the middle, since that's the one that's taking hot. That's probably the input. That must be off. Okay, pin 1 and pin 3. Go again. Off. Go again. And pin 1 and pin 2. So yes, it is a 2-way switch. You cycle through off and option 1 and option 2. So that is going to, let's see where that goes. So it looks like here, that looks like it goes underneath this pad over here. And that's option 1. And that goes directly to the base collector emitter. Let's see, pin 3 on this chip is the emitter. So pin 3 on the on the actual NPN transistor goes directly to the hot on option 1. So it looks like this takes in the hot side and throws it directly into that switch for option 1. And then we'll see now option 2's on. Option 2's on, so now we'll follow option 2. Option 2 goes right out the other side of the switch, and that goes directly to, let's see if I got it on there, check both sides, goes right to this diode right here, and it looks like the negative of that diode. Yes, so that's tied to the high side of this diode. And from the low side of the diode, we jump over these couple lanes. And we go to this resistor. And that resistor goes directly to the LED. Okay, so it looks like option 1 turns on both of these LEDs, and option 2 turns on just the center. We took option 2, that goes under the switch right out to the left side. That goes to a diode that jumps over these 2 lanes, and that goes to a resistor which goes to just this LED. So the this single LED is actually direct fed through whatever's coming in here. So it has a current limiting resistor, and this switch just turns it on like a normal circuit. But the other side, option 2, coming out the right side, going to the emitter of a transistor, that base going around the side to 3 diodes, taking in the wiring from the battery and the crank. And then the collector is going under here to the other 2 resistors, which go to the other 2 LEDs. So I happen to know that when you hook this up, you can see when I hook this up, we know that the lights that's option 1 with the single LED going out the left. We knew that. And option 2 turns on all 3 LEDs. So this transistor is only turning on these 2 LEDs, but the other single LED is getting power somewhere through option 1. So if we look over here, yeah, so if we want to find out how this third LED in the middle gets turned on option 2, we would go back to the resistor and go backwards from there. So we went here for option 1. We know that turns on through 1 resistor directly from the switch. But we know that this must get power from somewhere else. So what we need is to go back to the other side, follow this to the other side. Over here we have another diode, and that diode is also going to option 2. So when this is on option 1 and all 3 LEDs are on, it's getting power backfed through a diode for option 2. And then when you turn it to option 2, it's getting direct fed to the single LED. So it's physically switching between this and these 2. And this happens to be lit when these 2 are lit because it's backfed through a diode. So that's pretty much been broke wide open. What I'm going to do now is I'm going to go ahead and heat up the heat gun, and we're going to pop some components off of here and just kind of talk about them. So let's see, let's measure some resistance. Let's measure the resistance of the current limiting LEDs. Resistors, 41 ohms on that, and 150 ohms on the resistor to the base. And we're going to pop these diodes out, pop this transistor out, and I don't know, maybe we'll add it to here. Maybe we can we can make some kind of heavy duty switching circuit on here. You guys might have seen the video where I put this L1117 datasheet circuit together. I ended up pulling a little heat sink from a transistor off of that same dish cable box board, and cut the bottoms off of it, stuck it on there with a tiny bit of heat of a thermal paste, and globbed some solder on each side where I cut it off to help it stick, and it's on there. Let's see here, I'll grab my heat gun, turn it on to about 280. This doesn't look like super high voltage or high temperature solder, so grab my helping hand, pop it off. The original Sumsour heat gun I got, the one with the plain 2-dial display, 1 button, 2 dials, I think it is. The cheaper version of these 858D heat guns, that lasted 1 night. I reflown an Xbox 360 motherboard, and that night I actually heard the thermocouple inside crack, the glass thermal module crack, and it was getting way out of its boundaries. So I mean, this thing was glowing red inside when I first heard it crack, and then it stayed on. And then when I turned it off and turned it back on, finally the error code showed up and it wouldn't turn back on. But if I had just thrown it back on the stand, it may have never turned off. So I think that happened to EEV Blogs. Somebody he knew had one of those things, and he actually had the model I have, which is the nicer. This one's made by Yahuwah. It's about $10 more on Amazon, but it's definitely worth it. I've used it a whole bunch, and it's a 24 volt gun as opposed to the 120 volt gun. So the other 120 volt just had a surface mount transformer for nothing but turning voltage down for the display and stuff like that. So the actual gun itself was 120 volts, super dangerous. But this is 24 volt, just like the Schneider soldering iron I have. So it's a lot safer, a lot easier to regulate when you're not dealing with something that's, you know, balls to the walls and then off a million times a second, because you're never going to get an accurate reading with a cheap thermocouple like that. So actually, I gotta take that switch out first, because that is going to get nasty burnt. It already is. There we go. Now that that's out of the way, see if I can get these wires off too while I'm at it. There we go. Now we can take the main switch and start pulling that out. Solder's not too high temp, it seems to get loose pretty quickly. Come on, baby. See it moving the solder. There it goes. Come on. Come on. I'm getting too hot. Just pry it out of there. There we go. Alright, I'm going to give my heat gun a second to cool down. We got our chip out. Hopefully it didn't blow up from getting too hot. Looks okay. Got our button, which is absolutely dead. This button is dead. Yep. Okay, that's trash. That kind of sucks. That was a two-way switch too. That's okay. I didn't need it for anything. I'm going to take this barrel jack too. Cut that off. I might actually be able to use this for my EEPROM programmer with this, with a battery on this, two-way tape to the back. I might be able to stick this somewhere and have a charging port. So this is getting ridiculous at this point. Let's go ahead and cut the leads off. Actually, I'll leave those on there for right now. See if I can just strip them back a little bit. Oof. There we go. There we go. Okay, let's get our heat gun back up. I'll go ahead and pull this cap off. There we go. Nice electrolytic cap. That'll pretty much replace what I used the other day. Got wire off too while I'm at it. Keep stuff from catching on fire. There we go. Alright, start popping these resistors and LEDs and stuff off. These little components will come out really easy if the solder isn't too high temp. Looks like our LEDs are ready to come out. Current limiting resistors. There we go, that sucker did not want to come out of there for a minute. Still don't. There we go. Whew. Definitely want a fume extractor for this. I don't have one. I don't recommend doing this without it. Alright, give the heat gun a second to get cool. Got a nice little trove of components going here. I love this. I love knowing I have working components coming off of garbage. I mean, as you see here, even the trash. I mean, I mix it with some soil, and keep it here and keep it contained. I don't like just chucking plastic in the trash. I mean, since I've gotten into electronics, I've realized that, you know, there's a lot of effects from just having millions of tons of plastic fiber being dumped into the ground every year. It's kind of bad. So, very nice, very nice. Pull those off, keep that from smoking. I want to get plastic off of it. Obviously, I didn't do that at first, but it's a lot better if you do. I mean, it's kind of cool too, because this, I could always keep this little board, and if I found any way that these traces would work for me in any other circuit, I could solder suck all the holes back and use this board for something stupid. you know, I mean, this probably would have been doable on this, just because of how small it was and how little it required. Something to think about. Alright, go ahead and get that back in its coin. I like to pop it off the sleep tray for a second and put it back on just to get the fan moving without the element going. Okay, let's see if we can't get a few more components off of here. Try and get a twofer. Actually, I want this guy like that because I'm going to be pulling on, so. There we go, 2 for 1. Another. Once the area gets so hot, they just kind of start to fall out all at once. And honestly, temperatures, as long as there's not as long as it's not on fire and there's not electricity going through it, they can withstand pretty high temperatures. I'm just going to keep moving along here. Whew. There we go, last 2 components here. Come on, baby. There we go. Let that heat gun cool down. You can keep that so it cools down. Alright. Very cool. So the main thing that I wanted to do with this is get the components off of it and take a look at the main chip, and we'll go over the switching time test circuit. So you take an input voltage, you are resisting that to ground. You're taking a variable input from -5 volts up to the input, and then from there you're resisting into the base, and then you have a capacitor going from the -5 volt input on the other side of the variable resistor to the emitter, which is going to ground. From there you're going from ground over from a 470 volt microfarad to 25 volts. You're resisting that to your output. So here they're using the base to the collector to measure the time it takes for this to switch. So I'm not a professional. I don't know exactly how that works, but obviously they're not using it as a normal circumstance. They're using it in a way that measures base to collector. switch capabilities. So in a normal circumstance, this would be how it was on this board. You'd have the emitter going either permanently to high or being pulled high, and then letting the collector pull something low, like the low side of an LED, and then you have the high side of an LED going through a very small resistor, which we saw. And then from there you have all kinds of diodes that are basically working to keep the charging port, the crank, and the battery in sync, so that you're not blowing things up and reversing too much voltage. And not only that, you have to rectify the AC from the rotating body of the motor. Everything that rotates and creates electricity makes AC. You have to turn that into DC by using diodes in a diamond configuration, feeding it in the sides, and when you look at that diagram, you see that voltage can only flow one way. So you have a source and a drain, and your positive is obviously the back side of that because it's pulling the electrons through one way. So they are using, you know, what we saw originally with the 3 or 4 diodes that were lined up real close. I think that's what we were looking at as far as the rectification of the circuit. This does nothing but switch, and this particular transistor is way overbuilt for this thing. This will switch 60 volts off of a 5-volt saturation on the base. So it's way overpowered. I could use this with a heatsink to turn on I'm not sure how much amperage it'll let through, but I could turn on like a system as far as Xbox or something like that, something that takes a 12 volts with several amps. That may absolutely do it. So it's just interesting to see. This will switch 60 volts from a 5-volt base saturation, and they're using that to switch a piece of junk rechargeable survival light. So they spent way too much money on this chip as far as I'm concerned. And got some new LEDs to throw in the trucket bucket. And this capacitor is required for the activation of the emitter, and that's what they were using it for. You can see on the time test circuit in the data sheet that they do indeed have a 100 microfarad, and I think it's in the same spot as it was in the board. So yeah, that was pretty fun. I got some new components to throw in the jar here, so thanks for hanging out, and